Hi. So my name is Bill Buchanan, and I lead a podcast series on the world leaders in cryptography. And I'm so happy to have a true world leader with me, Rosario Gennaro. Hi, Rosario.
Hi, Bill. Thanks for having me.
Great. Rosario is a professor of computer science at City University of New York and a director of the Center of Algorithms and Interactive Scientific Software. In 1996, he received his PhD from MIT and was a researcher at the IBM T.J.Watson Research Center until 2012. Rosario's most recent work includes privacy and anonymity in electronic communications, along with proactive security to minimize the effects of system break-ins. He has received over 24,500 citations for his work and has an index of 72, and has published classic papers in non-interactive verifiable computing, outsourcing computing to untrusted workers, and quadratic span programs with succinct, non-interactive zero-knowledge proofs without PCPs, which we'll ask him about later, what those acronyms mean. So, what's your current role and what does a typical day involve for you?
Right. So I'm a professor at, as you said, at the City University of New York. So it's a typical academic schedule, right? I go to my office, I meet with students, I teach my classes, and I have some administrative roles that I also have. One is the director of the center that you mentioned, which includes other faculties and all our graduate students, and we organize events. We have visitors and all of that. But I'm also the director, the co-director of a new program that I started, a master program in cybersecurity at
Excellent.
which that also involves a fair amount of administrative work. So between classes and the little bit of administrative stuff that I have to do, I try to carve as much time as possible to do research, and that happens with my students, usually meetings with them, with my doctoral students, or I have to close the door and focus on a paper. I work from home 1 or 2 days a week, and those are the days in which I either read or write,
Yeah.
so that I don't have any interruptions.
Yeah. In this new course, do you have cryptography modules or cryptography related
Yeah, so
ones?
we do have a track which is more about cryptography. Yeah, so we also have system security, network security, but we do have a sequence of 2 to 3 courses that start from the basics and brings the students all the way to the most advanced topics. Yeah.
Yeah. And so what were your days at school like? Were you a great pupil? What were the subjects you
Are we
loved?
talking about
And
from when I was a kid
when you were
or grad
kids? Yeah,
school?
yeah,
I was
yeah.
always, yeah, I mean, yes, I was a great pupil. I was always a uh, top of, until I was in high school. Even college, I was maybe top of the class, the kind of student that teachers and faculty would point to as the person who to emulate, which sometimes I was proud, sometimes it kind of embarrassed me. College started being an interesting experience from that point of view because I started meeting people that were I wouldn't say smarter than me because I'm sure some of my high school and grade school classmates were smarter than me, but people who were working really hard. And at that point, I was just doing in Italy when you do. I'm Italian, and in Italy when you
Yeah,
go to college, you only do the major that you chose. So now I was just surrounded by mathematicians all the time. I went to college for math, and so that was actually an eye opener, how much other people knew and how much I had to sort of catch up with, right? And be so it was great. In college, although I was still, I would say, at the top of the class, but there were the doctoral students and there were the junior faculty that would be serve as inspiration, I would say.
yeah.
Yeah.
And why move from a beautiful country, Italy, to the US?
I moved for grad school. So I
Yeah.
graduated from college. And at that time, Italy had just started a formal PhD training program. There were no PhDs in Italy until the mid
Oh, wow.
80s.
Wow.
It was you graduated and then you would do this sort of informal training with a professor, a mentor, would sort of find some research funds, and you would be sort of like a research assistant, but there was no formal degree until the mid 80s. Although that had started by the time I graduated, my undergraduate advisor, Alfredo Ferro, who I owe a great debt of gratitude, because he had done his PhD in the US. He had worked at NYU. With Jack Schwartz. All of this name will come back later when we talk about PCPs and verifiable computation. And he really recommended that I would go to the United States for a PhD. And so that's what I did. I followed his advice and I applied to a few schools. I got into MIT, and MIT, you can't see your country may be as beautiful as you want, but MIT, you have to go. And and so that's why I moved.
Yeah. So I assume when you did your PhD, you were giving cryptography for the first time. Was that the first time you met it?
No. When I went to MIT, I was not yet aware of cryptography. I was actually planning to work on what's called computational geometry.
Yeah.
But I was interested in a aspect of computational geometry which was very algebraic. Sorry. I would so I when I was in college, I loved algebra. So that was my bread and butter. No matter how much there was a very, very pressuring faculty in the calculus, analysis that wanted me to work with them. But I loved algebra and I wanted to do algebra. And I discovered that through the advice of my mentor, that you could use this computerized decision procedure of algebraic equations and systems to help with geometric computational tasks. The most famous one is the piano movers problem, right? You have an object and you have a bunch of obstacles and you have to bring it from one side of the room to the other. And you can algebraize the entire thing, and then it's a yes or a no, depending if the system of equation has a solution or not. And so, and those are interesting tasks in robotics and also computer vision, computer graphic. So I was a mathematician. I'm still a mathematician. So those were great applications that I could see that the work had, but I was really interested in the math, in the algebra. How do you get a computer to solve this equation and decide if this is true or not? So that's what I was doing, and that's what I went to MIT to work on. And then I sat in Shafi Goldwasser's crypto course.
Wow.
And my algebra love, and Shafi, and then it was Silvio Micali's. The next class that I took was Silvio Micali's. Their infectious, I'd say, love for the discipline was just something. And I just fell in love with it, and I started working on that stuff. Yeah.
And that's amazing. So in all the areas of cryptography, you work on in so many different areas. What would you say is your favorite topic?
That's an interesting question. I have this sort of love-hate relationship with threshold cryptography. And the reason it's a love-hate relationship with it is that I I worked on it when I was in grad school. Ended up being my dissertation. And then, when you finish your dissertation, when you're towards the end, you sort of narrow your focus, get the thing done. And then all of a sudden you realize that there were all these little problems, research directions that you sort of took out of your mind because you needed to get the dissertation done, right? And so for a bunch of years, I worked on all these other things that were sort of left hanging from my dissertation. And then all of a sudden I decided I don't want to be known as the threshold cryptography person. So it was almost like a conscious decision to stop working on it. And unfortunately or fortunately, that's the thing came back with a vengeance when cryptocurrencies started, right? Because all of a sudden everybody cared about securing their wallets and doing threshold DSA, which was what I had done in my dissertation. And so all of a sudden, 20 years later, I'm back working exactly on the same thing, right? And so again, I was like, oh, this is great. Yeah, I love it. It's a bit, but then I was like, okay, I'm back in being pigeonholed into being the threshold cryptography person. So it's still one of my favorite areas. It's still the part that I navigate with more comfortable. When you give me a paper, I can probably understand it the quickest.
That's great.
Right.
And obviously, Audie Shamir's method is still beautiful.
Right. Every time I teach Shamir secret sharing to my students, I'm always in awe of the simplicity and the beauty of the idea, right? Yeah.
So what problems are you currently working on?
So I would say 2 or 3 right now. The biggest one, the one that is really taking a lot of my attention, and the ones that most of my students are also focusing on, is to try to use, we'll talk later a little bit about efficient zero knowledge proofs, but we're trying to see what is the limit of the feasibility. We're trying to push the envelope of the feasibility boundaries for ZK snarks when it comes to AI and neural network. So there's a lot of work. There's a lot of people that are working on this area, and so far the work has been, let's take the best zero knowledge proofs out there and apply them to neural network, and let's see what we get. And I'm, that's definitely something that you want to do, but at the same time, I think there is a need for a different approach. AI systems are so big that you really want to think about doing something different than just look at them as any other computation and put zero knowledge on top of that. And hopefully we'll get something that is a little better than what people are doing right now.
And because obviously you can use now homomorphic encryption with back propagation for a neural network, but I don't quite understand how the zero knowledge proof would.
Right. So homomorphic encryption will help you with privacy for the data, but what we're more concerned about is, suppose that you're supposed to use a specific model, right? And I'm buying predictions from you, right? So you're my AI agent that's going to tell me what to do on the stock market, right? So I have an interest to make sure that your answers are correct, right? And you may not want to reveal to me what the model is, but I want to make sure that the answer you give me are not different than the answer you're going to give to my competitors, for example, right? So zero knowledge proofs, and in this case, the zero knowledge is maybe to protect the privacy of your intellectual property, how your network works, or all of that. But what's actually more crucial here, more than the zero knowledge, is really the correctness of the result. So you're running a computation for me, and we'll get into that later in the podcast. You're running a computation for me that I can't run, and I need you to prove to me that you're doing the right stuff. And usually there is a cryptographic overhead on these proofs, and that is as big as the computation that you're running, right? And when the computation you're running is billion of parameters, like some of these large language models, it's a stretch to apply current cryptographic methods to it. So we're hoping, this is the direction that we're following with my students, that there is something specific about the way neural networks work, or like large language models work, that can allow us to build a different kind of proof. With some trade-offs, there's going to be something else to give, but maybe trade-offs that we can sort of accept, and then get in for the benefit of having a much better efficiency in terms of getting the proofs out.
I see. It's like the holy grail proof of computation. Prove to me that you've computed my sum correctly.
Exactly.
And AI, Gen AI doesn't give you that just now.
Right now, no. Right now, you sort of trust whoever is running the model for you, that they're actually running a correct model.
Yeah. Right. Okay, so but what's verifiable computing, and what do you think its core applications are?
Right, so we're actually basically got into already. So verifiable computing, back when I started working on it, my main focus of application was the cloud, right? So everybody rents an AWS server, put some code on it, put some data on it, and have Amazon run the program for them. And so then they get back the results. How do you know that that server ran that code on that data, right? And that is basically what verifiable computing is. You are giving you're offloading your computation to a untrusted provider. That comes in one of the titles of the papers that you mentioned, right? So you're offloading your computation and your data to an untrusted provider, and taking aside all the issues with privacy of the data that you're giving to the provider, let's just focus on the correctness of the result, right? So how do I get back from you a proof that the computation was performed correctly, the algorithm was run as supposed to? And the interesting thing is that I gave the computation to AWS because I can't do it myself, right? So when I get back this proof, I need to be able to verify the proof in time, which is substantially smaller than the time that it would take to run the computation itself. So there's this area of research in cryptography started in the mid-'80s of interactive proofs, in which you have a very powerful agent and who runs this very powerful computation. Back in the 80s, we were looking at exponential time computation, p-space computations. And then we have a lowly polynomial time machine, which is the verifier, a human who needs to be convinced that the result is correct, right? And it turns out that with the introduction of interaction and introduction of randomization, this actually can be done. This is the big contribution of both Goldwasser, Mikhail Rakov, and Babai. They won the Gödel Prize. They won several prizes for that. That show that very, very big computation can be proven to a very, very small machine just by adding interaction and randomization. And so basically what we started doing was me and the entire community of people who started working in this area was taking those results and scaling them down to the world of real life computation. So now big means polynomial, but really big, right? Yeah. And small means sublinear in the size of the computation. So you run something, but then you want your verifier to be constant time or log time over the size of what you're computing. So that's basically what verifiable computation is. As I said at the beginning, the very important application was making sure that keeping the cloud honest. Turns out that with the introduction of blockchain, this ended up having a incredible impact on the design of certain blockchain protocols and the scalability of blockchain protocols. So, for example, if you take Ethereum, the second largest blockchain system after Bitcoin, in Ethereum, there's this notion of a smart contract. What is a smart contract? A smart contract is a piece of code. And you run the code, and according to the output of the code, there's a money changes hands, say from me to you, depending on what this contract tells us to do. The blockchain system requires that everybody agrees on this output of this code and on this transfer of money from me to you, right? So what happens is, in a typical Ethereum transaction, is that the validators, meaning the entire blockchain, runs the computation. Everybody does it so that they can all agree what the output is, and they all agree that the money has to go from me to you because those conditions were met. That's incredibly wasteful, obviously, and that's one of the main reasons of the limited bandwidth capacity of Ethereum. So what happened, people started introducing this notion of layer 2. And I'm going to be very end wavy here. A layer 2 blockchain is basically a blockchain that runs the smart contracts for you, for everybody. One person runs the smart contract. And what they post on the Ethereum chain now, it's the output of the smart contract plus a proof that the output is correct. And if we're using these verifiable computations where the verification of the proof is much, much more efficient than the computation itself, now the Ethereum validators don't have to run the smart contract anymore. They just have to verify the correctness proof. And so layer 2 blockchains are actually improving the scalability of Ethereum transactions. And because the cost of the computation, it's an actual real cost, is the gas, the famous gas cost in an Ethereum blockchain. What's happening is that now gas costs are if you run things on layer 2, are much, much cheaper because you don't have to run the whole contract anymore. You just have to run the verification proof. Yeah. That was, and that like with threshold cryptography, the introduction of blockchain with all the money and interest that there is there really, really brought a lot of attention and a lot of investment into this area because people really, really care about it.
Yeah. So a lot of it is really trusting off-chain. So rather than running things on-chain, you want to offshore to cheap processing resources to do it for you, to come back less gas, and you can still trust it. So the proof of work comes back. So I suppose the key thing here is now the non-interactive element of this. With a zero knowledge proof, you have a challenge, and then you create the zero knowledge proof. So obviously you want a non-interactive zero knowledge proof. So how does that work?
You hit the nail on the head, right? While on the cloud, I could engage with Amazon on a back and forth, right? that says, well, you're telling me that this linear regression that I sent you on this massive data set is what it is. Well, let's talk a little bit and convince me, right? But in the other application that I mentioned, the computation really has to come back with a certificate. There can't be any interaction. So there's the computation, there's this proof that says the computation is correct. It cannot be interacted because everybody in the Ethereum network has to verify, right? And so that would mean everybody will have to start talking to the person who did the computation, which is not feasible. So yeah, so you definitely need non-interactive. And depending on what the smart contract does, you may need zero knowledge. Actually, most of the stuff that is happening right now in layer twos, they call it ZK, but it's not really ZK. No, right? And it's not actually even needed to be ZK because the computation is all public. There is no secrets there. The ZK comes from the fact that you're really compressing everything down to very small proofs. And so, but there is no need, and not actually, some of the schemes are not even zero knowledge because it's not needed.
No, that's interesting. And we move from discrete logs onto elliptic curves. So everything we've built in blockchain and our crypto world is elliptic curves now because it's so efficient. But obviously quantum computers are coming along like are not. So we have all these amazing primitives, as you say, the secret shares and so on. And obviously we need to translate those into this new lattice world. Lattice is now quantum robust. So I think you published work on ZK snarks, which are lattice-based, and it just blows my brain. I just
when I saw that question, I almost I take it off. But actually, it's a good place as many to mention it. That paper actually is not. It's broken actually, and the reason it's broken is that. So let me tell you, that paper comes. I think. So there's another paper that I wrote before, which is this quadratic span programs. I think you were going to ask me about that too, right? So this is a paper that it builds one of these efficient proofs. It was the first paper that showed how to do this with a constant size proof. So now, no matter how big your computation is, you have a proof that is constant size and takes constant time to verify, which is amazing. And in fact, a lot of the blockchain companies went and used this scheme. Well, they used an optimized version due to Ian's growth. In fact, everybody refers to it as growth 16, but it's really an optimization of this old paper. So we started, I was in Paris and I started talking to two students there. How do we do this with lattices, right? We don't want to be stuck with desk log. And it was a short visit at the École Normale, but it sort of planted the seeds, and we eventually wrote this paper. And all we did was sort of mimic the paper, the QSP paper, the Quadratic Span Program paper, to the world of lattices. And in the Quadratic Span Program paper, you need what's called, you need a way to sort of encode information with something which is additively homomorphic, because that allows you to, but it's not, it's hard to do the multiplicative homomorphic. So you do something like Payet or desk log in the exponent, all of that will work. In fact, the Quadratic Span Program talks about both Payet and desk log as ways of encoding this information. So we started building this encoding that has and with lattices that give you fully homomorphic encryption, it's a little harder to build this this encoding, but we did, and we made an assumption. We made an assumption about the security of this encoding that we built, and then this assumption was also used in other papers. And then a few years ago, not pretty recently actually, that assumption was actually proven to be correct. And it's not the assumption was a very strong assumption, so I'm not surprised. So there is an assumption that we used a lot in, which is that if I put a polynomial, if I give you g in the exponent of a discrete log, so I give you g to the something, and I give you several of them, and they're polynomially related, then I need to know that polynomial. I can come up with g to the polynomial evaluated without knowing what the polynomial is. And we made a similar assumption for our encoding based on lattices. Turns out that with lattices, because of the noise and all of that stuff, that assumption was false. So the paper, I don't think it breaks the paper, but it breaks the proof. So so the paper is in a sort of gray area right now, and I wouldn't recommend using it.
I suppose the problem is that we need to replace pairing-based cryptography with something else. That's the kind of core to a lot of these methods.
So there is a fairly active. I haven't followed this since that paper. There's a fairly active research area that looks at exactly this, trying to mimic what happens. What kind of property you need from discrete log or pairings to get this efficient zero knowledge proofs and replicate them with lattices. And it's hard, and there's also an efficiency concern about how big lattices are, especially in an area where you want the proofs to be really small, right? Because you post them on chain, and so they need to be as small as possible. But it's something that we have to do, right? As you were saying, sooner or later we're going to have to deal with the. I used to be a quantum skeptic, and now I'm kind of not. So that's something that we have to do for sure.
Yeah, it's difficult. I mean, it's been 50 years with discrete logs and elliptic curves and so on. So we need a change every now and then.
Right.
So what's a quadratic span programs with succinct zero knowledge proofs without PCPs?
Right. So without PCP, PCP is the culmination, stands for probabilistically checkable proof, and it was the culmination of the interactive proof work that started in the 80s. So in the 80s, the interactive proofs meant that I have this large computation, there's the small verifier, we talk, and with randomization, we eventually figure out that the computation is correct. PCP came sort of in the early 90s. Now the prover just writes down a proof that the computation is correct. And this proof could be long, but the interesting thing is that the verifier only has to look at a few locations of these proofs and to be convinced that the proof is correct. And so this was an amazing breakthrough. It came out of the IP equal to space and sort of the introduction of the sum check protocol and all of that stuff. So turns out that once you have PCPs, there's a next step is you can build zero knowledge proofs by first committing to this large proof into a single. So now the prover says, here's the proof, but it might be too big for the verifier, right? So the prover just uses cryptography. PCPs are information theoretic. There is no cryptography there. It's just there. But now use a commitment scheme to make it very small and give it to you, right? And then we use a commitment scheme that I can open individual locations. So the typical example is a Merkle tree. And this was an idea due to Killian and then eventually to Silvio Micali. And then we open a few locations in these proofs. You verify a procedure to determine if the proof is correct. And now we have a we have what's now called a SNARK, a succinct, non-interactive argument that the computation is correct. So the QSP paper was, I like to think, the first that deviated a little bit from this paradigm. There were other work by Ishai, Shilevitz, and Ostrowski that also started to look at similar ideas that started to do something different than this idea, to use PCP, compress them, and then and the idea is that, and I was sort of actually not happy about the sentence without PCPs in the title, because what I actually wanted to say was this is a different way of building PCPs. I mean, PCP is an idea. It's a different scheme. So it's not that we're not using PCPs, we're building PCPs in a different way. But whatever, the title stuck. So QSPs basically take your code and map it into a algebraic system of equations. And remember what I told you about what I was working on when I was an undergraduate, okay? Because it's sort of very similar idea. And then you have this polynomial equations, and you need to determine if they're consistent, basically. And what the idea of the paper is exactly to sort of force the prover through cryptography to show me that there's no way that if they're inconsistent, then you can't convince me that they're consistent, that they are. So and we were able to use this encoding schemes that I was mentioning before to give you a constant size proof. And the idea is really revolves around, which is also crucial in the PCP theorem. That's why I thought this is really not without PCPs, but on this very crucial lemma, which is the Schwartz-Zippel lemma, that says that if you have a very, very large polynomial, and you want to determine if the polynomial is identically 0 or not, all you have to do is test it on a random point. If it's 0, then you're pretty sure that the polynomial is identically 0, because a polynomial of degree d has only d roots, right? And so if you choose your random point on a very large domain, the probability that you're hitting a root is very, very small. So, and basically that's one of the ideas in the QSP paper. We force the prover to use a random point to evaluate this system of polynomial equations. And if the polynomial is 0, then we know that the result is correct. And the forcing of the prover comes from that encoding, which allows you to do additions, but it doesn't allow you to do multiplications. Because once I give you, so I have the polynomial, I give you encoding of this random point at all the powers. So I give you the encoding of s, encoding of s squared, encoding of s to the d, where d is the maximum power of the maximum degree of the polynomial. Once you have all those encodings, all you can do is addition. You can do the additions, that's enough to compute the polynomial, encoding of the polynomial. But if you want to cheat, we can show in the proof that you have to compute an encoding of s to the d plus 1, and that's not possible because of the cryptography behind the encoding. So that's amazing. That's basically the idea.
Yeah. It's a bit like a teacher giving a problem to their pupils. And rather than asking for the answer, all of the pupils can provide their proof of computation.
They know the answer. Exactly.
What an amazing concept that would be. Right. So none of them reveal the answer, so there's no cheating going on, but everyone will come up with a different proof.
This is, again, goes back to the amazing introduction of zero knowledge proofs, right? Yeah. Such a counterintuitive notion, but it totally goes back to that. Yeah.
And how do fully homomorphic authenticators work?
So that was so the zero knowledge proofs are usually something that everybody can verify. But sometimes maybe this is back to the cloud kind of setting. Maybe I gave you some data, right? And I'm storing this large amount of data on the cloud. And I am interested to ask you some, statistics, some aggregate, some computation on this data that you're storing for me. And you give me back the result. Again, how do I know that you did correctly? With an authenticator, now I can be convinced the result is correct, but it's only something that convinces me. It doesn't necessarily convince it's the difference between a digital signature and a MAC, right?
Yeah.
So a digital signature, you sign your message, everybody knows that you signed the message. If you and I have a key in common and you MAC the message for me, only the two of us can verify that the message is correct. And MACs are much more efficient than digital signatures, right? So that's basically the idea. It's basically a private or one other terminology that people use is designated verifier way of proving the correctness of a computation, but rather than being publicly verifiable, is just for the person who has the key that can verify it. In the case of verifiable computation, I don't think there has been much difference in the efficiency between the two. And so that's actually, when you ask me, one of the things that I'm working on, I have a student that I want to sort of test the hypothesis that maybe it's possible to build private key authenticators that can maybe be an order of magnitude faster than publicly available verifiable snarks for computations.
And obviously, one of the big areas you work in, your love-hate relationship with threshold cryptography, and the dream would be to create private keys that never really existed. Anyway, I know that can't actually really happen, but that would be the dream of this completely distributed system where you can have consensus, you can shard the key, and so on. So can you just outline how distributed key generation works, and can it ever be fully trusted?
Well, I mean, in cryptography, we can't ever fully trust anything, right? There's always an unproven assumption. So right now, we're all, hoping nobody has a quantum computer. We're all hoping nobody's developed a factoring algorithm, right? So there's always that kind of assumption. In the case of distributed key generation, there is also the threshold assumption that at least one party has to be honest and not share and not collude with all the other parties to disclose the secret key, right? At that point, once you have at least one person that is honest, that is going to follow the protocol, then the idea of a distributed key generation is actually pretty simple. And then the complications all come from trying to make it as efficient as possible, is that we all generate a key together and each of us contributes a random component to it. And the nice thing about Shamir is that you can add things very easily. And so if we do Shamir, the easiest way to do it is I choose a random number, you choose a random number, Tal chooses another random number, and we all do a Shamir secret sharing. And if we locally add the shares that we received, that's a share of the secret determined by the addition of all the original random contribution of every claim. So now the key is that value that nobody's ever seen because I've only determined R1, you determine R2, everybody else 3, 4, 5. And so nobody knows unless everybody colludes. But again, we're assuming that there is a person who's not going to do that. So that's basically the idea. And in the case of Descott-Log schemes, you also have to do it when you sign, right? Because every signature in Descott-Log schemes includes the generation of a random nonce, and usually that involves a a DKG as well, right? So, and then you have to do it when you do proactive, which means you want to refresh your share so that maybe this person is honest today, but gets infected, but then you assume that maybe tomorrow this person is the honest one, right? So you want to make sure that no matter who the honest person is, as it travels around the network, security is still preserved.
Yeah.
But every time you do basically a refreshing of the share by doing another DKG.
Yeah. And obviously with signatures, we have RSA. It's still the king of the hill, like or not. It's still one of the most popular signature methods. But ECDSA and ED-DSA are the two main elliptic curve methods. ED-DSA is wonderful, but it was held back by the SNOR patent,
Right.
and the industry just didn't use it. Satoshi Nakamoto came along and selected the ECDSA,
Right.
which was based on the horrible DSA patent that got around the SNOR patent. And it was assigned, I think, to the people of the US, so there was no patent problems. And then we adopted the ECDSA, and it's really held us back. But obviously, Ethereum and Bitcoin are all based on ECDSA. So, and I know we're struggling to find a threshold signature scheme for ECDSA because we want to apply it into Ethereum and blockchain generally. Do you think we'll ever find an efficient threshold scheme for ECDSA, or should we just go straight to ED-DSA?
I personally, in spite of having built a career in that, I think we should move to ED-DSA. I mean, if I were to design something today, I would do ED-DSA. That said, I think the question of pushing the envelope of ECDSA, threshold ECDSA, is incredibly interesting. We still don't know, for example, how to do it in one round.
It takes many rounds.
Incredible. And I think, so Yuda Lindahl has been doing some really exciting work in the area. And some of the work has interesting concept, interesting techniques. So I don't think we should stop working on ECDSA. If anything, because the insights are interesting and can be used in other areas. So I don't think we'll ever be faster than EDSA when it comes to threshold, but I don't see that as a reason to stop working on it.
It's ED-DSA is a FIPS standard now, FIPS 186, I think. So there's nothing to stop industry from using ED-DSA.
So I may misspeak here, but I believe there was a Bitcoin update that also allows them to use Schnorr or ED-DSA for
a multi-sig approach.
For their signature,
Yeah. Because I think there are new multi-sig approaches which are a bit more complex than the Bitcoin implementation. But I think they use the ED-DSA approach. Just needs a bit more complexity. And so, what's fully distributed group signatures, and what's their main applications?
That's actually it's very obscure. So a group signature group signatures were proposed by Chown way back. And the idea of a group signature is that there's a group, and anybody in the group can sign on behalf of the group. And so there are two special characters in a group signature. One character is they're called managers. One is the manager that decides who are the members of the group. So if you want to join the group and you qualify to join the group, the admission manager is going to give you credentials to get into the group. Now, what a very simple solution for a group signature is that we all have the same key, right? There's one public key and everybody gets the secret key. And now everybody can sign on behalf of the group. But in group signature, you want also what's called a de-anonymization manager. You want a manager who's able to, in case of abuse, in case of disputes, determine who was the person in the group that signed that message. So unless this manager gets involved, nobody knows. It's a signature. It looks like it could be anybody in the group. But if there is a problem, this manager can determine who the group person is. So both managers are obviously trusted, right? In some level. One is trusted because they know everybody. They know who signed. They can de-anonymize any signature. And the other is trusted because he may prevent you from getting into the group. We may censor you or whatever. So usually when you have a trusted party, the approach of threshold cryptography and multi-party computation in general is to thresholdize that party. Replace it with a group of parties where you assume that a fraction of them, at least one, is honest. And at that point now, this person, there is no single person who can compromise the security of the scheme. So when group signature were introduced, the managers, both managers were trusted. Turns out that thresholdizing the admission, now I remember actually, was it the admission or was it one of the two managers was easy to thresholdize? It was, right? The other manager was slightly more difficult. So yeah, I was actually surprised when I worked on this maybe about 10 years ago that there was no simple way to turn this trusted party into a because usually the way group signature works is that I encrypt what you have is an encryption of the secret key, each party, and this allows them to encrypt the signature and prove that the signature is correct. That's basically what a group signature is. And then to de-anonymize, you decrypt the signature. So there was some complication there in making sure that you could do a threshold version of that. But this basically was a fully decentralized, a fully distributed group signatures where both managers are distributed and not just one of them.
Yeah, that's interesting. So really, you're basically flagging that it was me, but you can't see it. Only the trusted entity can see the flag.
Right, but the trusted entity could convince, could produce a undeniable proof. So it could bring you to court and convince a judge that that signature really came from you.
Yeah.
So, and the idea is that with a threshold de-anonymization manager, you don't do that unless there is actually a dispute. Well, with a single party, this single party knows everybody who, every signature knows who produced it, right? So, yeah.
And there's a great debate about central bank digital currencies just now. So there are some countries, such as China, where it's a centralized ledger and the central bank can see everything. But obviously, in a more perfect world, you still need to check for money laundering and crime and so on, but you don't want to see everyone's transactions. So I think an application area that you're outlining is to have the opportunity to at least go back to transactions, and somewhere you have a trusted auditor. They would say, okay, that was crime. Let's actually have a look at that one. But generally, the central bank couldn't actually see all of the transactions. I think the way that China has went is obviously probably not the way that other countries would go with this, because there are so many privacy concerns. But that flagging is really quite interesting.
Right.
That only one entity.
The interesting thing is the group signature really comes into play for what are called anonymous credentials.
Yeah.
So if I have to show that I have a driver's license, why do I have to show you my name, my address, maybe I can just show you that I have a driver's license, right? Yeah. I can get this car because I have a driver's license. You don't need to know who I am. You don't need to know, right? So That's basically a group signature. I sign a message on behalf of the group, the holders of a valid driver's license. Then a crime happens with that card, right? At that point, you want to de-anonymize that person. By having this manager distributed, you are still allowing some sort of accountability, but at the same time, you're preventing the abuse that now this manager would know everybody's private data instead of just knowing that they're allowed to drive a car. So this work that Jan Kamenisch and
CL signatures,
they worked. Jan and Anna Lisyanskaya Brown, they've worked.
I spoke to her recently too, and amazing work that she did. I think it was at IBM. We'll come back on to IBM a little bit later. So what's an escrow protocol for cryptocurrencies?
Yeah, so an escrow protocol for cryptocurrency is, so let's assume that I give you money in exchange for something, right? So how do you do that? This is it's a typical problem in computer science called fair exchange. I have to give you something and you have to, I give you goods, you pay me, right? Two-party fair exchange is impossible in the sense that if one of the two parties is malicious, there's always the possibility that I give you the goods and you don't pay me, or you pay me and I don't give you the goods, right? So the person who speaks first in this exchange may always end up being stiffed. So in the way to address this is to introduce a trusted party, which makes sure that the fair exchange happens fairly. And this trusted party usually takes the money in escrow. So I put the money in escrow with the trusted party, you give me the goods, and the trusted party sends you this is actually not an ideal solution because the trusted party is now involved in every single transaction. There's a version of fair exchange which is called optimistic fair exchange, in which unless you and I complain, the trusted party is never involved. So you and I, the trusted party is not involved if the transaction happens normally and succeeds, but if something happens, then the trusted party gets involved. Because cryptocurrencies do a lot of transactions of this kind, there was a need for an escrow agent, and the escrow agent had to be somehow also, you need to trust it. And as typical approach, what you do with a trusted party, you thresholdize it. You make sure that instead of trusting a single person, you trust a network of people where at least one is honest. That sort of brings down your security assumptions. So an escrow service for cryptocurrency is usually a network of a few parties that will do exactly that, take your money in escrow and release it when the transaction is finished. But instead of being a single party, they usually do a multi-signature or a threshold signature to make sure that the funds are sent out.
I saw a good example. Someone made a bet on a soccer football match, and it was a mistake. The betting company put the wrong odds on, something like 16-1 for this team who was losing 3-0 to win, and the person won the bet. And then the betting company said, well, it's not void because it was a mistake on our side. You will not get the bet. So obviously there should have been some escrow there to be able to decide if the bet was correct or not. And just by making a mistake was incorrect. So I think a lot of this settling contracts will need some trust. We call this a solicitor just now, some legal representative who will hold the money to people purchasing. One person purchasing a house, you would put the money in escrow to make sure that everything.
Yeah, I mean that happens here in the US too, right? You put money in escrow with a lawyer, and then that's basically trying to replicate that in the world of cryptocurrencies.
That's right. Okay, you've also worked on deniable authentication.
Uh,
It seems like the opposite ends, deniable and
right,
authentication don't
right.
quite go together. So what's deniable authentication and key exchange, and what are undeniable certificates?
It's actually not related, but let's start with deniable authentication because
Mm.
that's really it's actually in the news a lot today because of the use of signal by certain parties. And so, in deniable key exchange or deniable authentication, I send a message to you and you know that the message came from me,
Mm.
but you are not allowed to prove to a third party that that message came from me. So
Yeah.
now, if you and I exchange a key, we just talked about it earlier, right? Um, if we have already exchanged the key, then I can just mark that message with the key. You receive the key, you receive the message with the MAC, you verify the MAC, you know the message came from me. Why do you know that the message came from me? The MAC says this message came from somebody who knows the secret key.
Mm.
And you know that the only two people who know the secret key is you and I. You didn't produce the message, it must have come from me, right? So that's why you believe that the message came from me. But what if you and I don't never met and don't share a key? Is it possible for me to convince you in a way? So I have a public key. Can I produce a tag to the message that convince you that this is coming from me uh, without then you being able to go? If I digitally sign that message, that's it. You can prove that, you can show that to anybody, right? So this was work that started. It's very interesting. It started really at the same time in the theoretical community. There was a paper by Duarte and Naor on deniable
Yeah.
application, and
Yeah.
I think Amit Sahai. But at the same time, the networking community, the security people were also very interested in working on that, and they started talking about this um, um, off the record. At that time, we had all these messaging apps. Like there was, we're still in the time of Yahoo Messengers,
Yeah.
AOL Messenger, and they were building these plugins that you could put into Yahoo Messenger or AOL Messenger that would turn your messenger into an off the record, so that you wouldn't be able to show other people that the messages came from me. And so so one thing that we worked on with Ugo Krachek and one of my doctoral students at the time, Mario Di Raimondo, was, well, like with digital signatures, right? We don't sign every message that we send to each other. We do a key exchange. We use
Yeah.
digital signatures to authenticate the key exchange. And then we have a communication session in which you and I exchange messages.
Yeah.
Um, so we started thinking about, okay, how do we do that? How do we create a, once we are in the in the session with the private key, we're done. We know it's deniable. So what we need to really make deniable is the key exchange part, right? Because then you wouldn't even be able to prove to a third party that you have started a secret session with me. Um, so that's basically what we did. We showed how to combine deniable authentication with classical key exchanges and come up with a notion of deniable key exchange. That once you put it on top of any communication session, the entire session now becomes deniable in the sense that
Yeah.
neither you or I can prove to a third party that we engaged into that session.
Yeah. So it's very much privacy aware.
It's
So
totally
uh,
it's
the contract is between me and you. I can prove you signed it, but if I show you this to someone else, they will not know it was you that actually
Yeah,
signed
and the
it.
application that that time was off the record communication for journalists, for whistleblowers and all that stuff. You can, if you're afraid of any kind of repercussion from your communications with sensitive parties. Yeah.
And it's obviously a big topic just now, WhatsApp, Signal,
Yes.
Telegram, and so on. And we have this tension with governments trying to create backdoors and things like that. So what's cryptographic deniability in the Signal protocol?
So the Signal protocol came later, and so the basic idea of how we suggested to do key exchange was for you to be convinced that you're talking to me, instead of me digitally signing something, you send me something encrypted, and I will decrypt it for you. And I do the same with you. And then the key that we're going to use for that session is a combination, the exclusive OR of the two random strings that we send to each other, right?
Yeah.
Now, at this point, and I'm waving a little bit, at this point, we know that the key is only something that the two of us know, because I sent you the key, I sent you R, and you decrypted it. Right? I sent you R encrypted and you decrypted. You send me S encrypted and I decrypted it. And R plus S is our key. Great. We know that only the two of us can do it because the public keys associated with us were used to decrypt these messages. But there's no way to convince a third party because I can simulate the entire transcript on my own, right? I know both R and S. R because I created, S because I decrypted it. There's no trace that I talk to you, except that I'm using your public key, but I could pick your public key anyway. Signal basically does the same thing, where the encryption is the Diffie-Hellman key exchange. So you and I, we have our long-term Diffie-Hellman keys. We do a Diffie-Hellman key exchange with fresh keys. And our key is the combination of all. If you think about it, there's now 4 Diffie-Hellman keys. Ephemeral with ephemeral, long-term with long-term, ephemeral with long, and ephemeral with long. They discard the long-term because it doesn't really help. And they make the key the hash of the other 3. In fact, it's called a triple Diffie-Hellman protocol. By the same token, by the same argument that this protocol is deniable. Okay. Well, turns out that so this Signal came out about 5-10 years after we wrote this paper. Turns out that when we wrote the paper with the encryption part, we did think about something like that. And we had actually a section written in the paper with a proof of deniability, with a proof that there is this simulator that can build the entire key exchange without talking to you, which means there is not proof that I talked to you. And then it was actually my student, Mario, who 2 days before the deadline, so that there was a gap in our proof. It was 2 days before the deadline. The only thing left to do was we had the basic result. This was just an instantiation of the basic result. We took it off. I still have the file with the ignore comment in the later body, in which that section went off the window. The paper got accepted, great. I didn't think about it. Then 10 years later, 15 years later, I'm talking to another of my doctoral students, and we're talking about Signal, and she's telling me what Signal does. And, this vague memories start coming back in my brain. And I said, well, it's deniable, right? So I said, yeah, it's deniable. I said, oh, where's the proof? At that point, I didn't even remember that our proof had a gap. So it wasn't even like, and turns out that there is an intuitive explanation of the deniability of signal, but there was no formal proof. And the reason there was no formal proof is that I don't know if the signal researcher and engineers actually tried. They might have been satisfied with the informal explanation, which is the informal explanation is that this 3D filaments, I could have built them myself, right? I could have built the two ephemerals like coming from you, and then I could have used your public key to just compute the three. Well, turns out that this is true if my ephemeral is honestly generated. But if I generate my ephemeral in a weird way, that is not clear anymore. And that's exactly where the gap in the proof was. When I realized, and then as we were talking, I was like, wait, this sounds familiar. Because that's exactly what when my new student, that's I sound familiar, I went back to the paper, I went and pulled out our skeleton of a proof and realized that there was this gap. So I gave it to my student and say, look, this is something that we didn't do. So it's a hard problem. If you want to take it on, take it on. And she, I have to say, Nihal Batandas, she was amazing. She said, I'll take it on. And we worked on it really, really hard and came up with I brought back Hugo into it because he was also interested, Hugo Krakchek. And we wrote a proof. We figured out a proof. It requires a much stronger assumption on the security of the Diffie-Hellman scheme, but it is deniable. So, and I never doubted for a moment that the protocol was deniable. It's just that there was no proof, and I wanted to see a proof. And so we wrote the proof, we wrote the paper got published, and I'm very happy. It's one of the things that actually I'm the most proud for this ability. I'm proud of my students, first of all, but I'm also really happy that we sort of settled it, because at some level in my brain, it was still bothering me that we had sort of dropped that proof. And here's an interesting thing. Signal is already deploying the post-quantum version. And the reason is that with quantum, you have this harvest now, decrypt later, which means I'm going to store all the encrypted communications. And when I finally get a quantum computer, I'm going to find out what everybody's been doing. So it makes sense, at least for encryption, to start using post-quantum now. For authentication, no, because authentication is time sensitive. There's a freshness issue. But for encryption, we better start moving to quantum resistance now. So there is an option in the Signal app to move to the post-quantum triple Diffie-Hellman. And again, what they're doing is mimicking what happens in the Diffie-Hellman key exchange using other key exchange based on lattices. So I think it was last year, I saw a Twitter post in which they announced it, and I went to look at the white paper, and there's a very interesting sentence in the white paper that said that our proof of deniability for the Dasky log does not actually transfer to the new version. And that, you asked me at the beginning one of the things that I'm working on is trying to understand why the proof doesn't transfer. I know other people are working on it, and that might have changed by now, so I don't want to claim that it's still open. But it's interesting to me that the proof doesn't carry through, and that's actually to do with lattices, and again the noise and all the complications that come with lattices. So it's interesting, right?
Because obviously MLChem isn't Diffie-Hellman anymore. It's encapsulating with encryption. So you're encrypting with the public key. You're creating some seed to give you a secret value that's encapsulated, sent over. So it's really difficult to just scale that into Diffie-Hellman. I think Psych was one that could integrate isogenies into a Diffie-Hellman type exchange, but really we need to stop thinking about that.
Right.
And 2001 must have been quite an exciting time for you. So that really changed the world of cybersecurity. NIST defined the AES standard And there was many competitors for that, of which Raindao actually won. So I think you were part of the Mars team. So what was the history of Mars, and why do you think it just didn't get quite there?
Yeah, so I was part of the Mars team, but I say I was maybe I wasn't one of the crucial members of the team. I mean, Shia Levy and Chanjit Chukla were really the main designers on Mars. I don't know what happened. I know we were finalists. I think Mars had, in the comments that we received, had this idea, this impression that we were throwing the kitchen sink at the problem.
Yeah, yeah.
So I think
Lots
we
of
got this,
security.
yeah, we
Yeah,
got this
that
kind of
was it.
perception that we, I think the sense that people got, which I disagree with, there were very clear design choices that we made, and we were very conservative with the security. But what happened was that I think the perception was that we were putting so many layers into it that it was almost like we didn't trust this layer, so we put another layer on top, and then we did, which it's one of the tenets of conservative design, right?
Yeah,
But at the same time, it felt like the perception from the outside was again this idea we're throwing the kitchen sink because we don't know exactly which one is working, which one is not. So I think that was one of the things. And then I had to say the AES Rindell came out of left field. You know, they went back to the substitution permutation network rather than Feistel ladders, and it was a completely revolutionary design. So it's kind of surprising that they chose that because how
different.
revolutionary
Yeah,
it was, but you know, at the same time, it's very exciting. So while Mars was a much more conservative, stayed, like, I mean, in a way, that was one of the design choices that we made, right? This is the NIST would probably want to go for something tried and true and tested, and right, and I was actually surprised that they went for a design that was a little off. Although it's still in a line of research which was very clear, the substitution permutation network. But and I think we can tell that it was a good choice, right? It was a right choice.
yeah,
The AS has been
yeah.
not suffering for any particular weaknesses. So I think one of the things that I did in the Mars once the candidates came out, I took up upon myself to sort of really trying to figure out if there were any weaknesses in AES. And I was zooming in into this. There are a few algebraic components,
Yeah,
because I like algebra. And I was
yeah,
zoomed in on the way some of the S boxes are computed
yeah,
using very clean algebraic structures. I remember having sitting with Don Copsmith, who was obviously a legend, and trying to say, coming up short every time. You know, that this doesn't work, and this doesn't work, and this doesn't work. So I think at the end it was the right choice.
yeah, yeah. And obviously, performance tends to win. It's trying to find that balance between security. The more security you throw at it, the slower it gets, the more energy it consumes. So it's finding that right
Then
point.
I think actually Mars actually
Yeah,
for the kind of conservative design and um, the benchmarks were actually pretty good, I thought.
yeah,
But again, I think AES was
yeah,
way up there.
yeah. And it's strange now that they're now coming out with two or three. I think HQC has been approved for the key exchange, and for
Right.
digital signatures, you've got quite a few. You obviously have the
Right.
MLDSA and
Yeah.
the Sphinx Plus and so on. So they now have alternatives where with the symmetric key encryption, they didn't. They just went for
Right.
one method, which was
Right.
risky, as you say. So I think you worked with an amazing team in IBM, such as with Tao Rabin and Craig Gentry. What can you remember of some of the things that you worked on there?
So it was interesting because before Craig came, there was four of us. Me, Tal, Shia Levy, and Rankanet.
Wow.
And there was Hugo who basically brought us all in, and then Hugo left. And then eventually Hugo came back, but he left.
Yeah.
And the interesting thing about the four of us was that we were all at MIT together. Shai and I were students of Silvio Micali, and Tal and Ran were postdocs there. They finished their PhD in Israel, and they come to MIT. And so we had already spent a lot of time together at MIT.
Yeah.
And then we all moved as a block to IBM. So it was really incredible how we didn't miss a beat. We went from one place to the other and kept really working on things. So yeah, threshold cryptography was one of the things that we worked a lot in those days. And the interesting thing about being at IBM was how there were these conversations with the more developers kind of people, still in research, but more interfacing to the product division. And so there were these questions, and the question usually had three way of answering it. One was, oh, read this paper or look at this book at this pages, and you'll find what you're looking for. So we were in a way repository of knowledge for IBM. The other one was, I don't think, you sit in front of a board for about a few hours maybe, and you solve it. This is how you do it. And then there were the very interesting ones, right? There were the ones, oh, I don't know how to do this. And then you would write a paper about it, like you sit about it. Then it became a real research question. That was actually what was very interesting from working there, right? It was this kind of interaction. And one of the things, actually, this is something that I didn't work with Tal, and I worked with one of the network security people, was this idea of streaming. How do you sign a stream, right? So you sign the head, and then you embed blocks, and so actually the idea of a blockchain appears in that paper. That you can sort of link every block of the stream through a hash, and that's enough to sign the entire stream. So those are the kind of interesting things that came up. And then Craig came, and of course, Craig's most amazing thing is that he wrote the fully homomorphic, solved fully homomorphic as he was summer intern at IBM.
Amazing.
It was remarkable. And then when Craig came, there was a lot of other stuff that we started working. I mean, like the QSP paper and this verifiable computation was definitely something that I started working with Craig when he was there. We started looking at how can you use fully homomorphic. There was a paper before the QSP where we used fully homomorphic encryption to somehow encode the computation that you are performing, and then come up with a proof. So we were using it not for privacy reason, but more for authentication, so to prove correctness. So it was just incredible to come to work and have all of us like next to each other in the rooms and read a paper, and the ability to sort of get up from my desk and walk to the other office and say, I don't understand this. Have you read this paper? Do you understand it? And no, I don't understand it either. And then at that point, we would just sit in front of the board for 2 hours until we figured it out, and then as you're trying to do that, questions come up. That's how research happens, right? Research a lot of the time happens from serendipity. You read a paper, you have a question, you go ask, and then that conversation takes you somewhere else, right? So it was a really incredible place to work.
So why move from industry into academia? I know that IBM research was a bit like academia without the teaching and the admin.
Right.
But
right.
why did you make the jump?
two main reasons. One was personal and one was professional. The personal one was I had just that two kids. I'd adopted two kids that were very young. I was looking for. I grew up with two parents who were teachers. They were grade school teachers. My dad became a principal. My mom was always a teacher, but they had most of the summer off. My parents had most of the summer off, and we had the most amazing adventures in the summer. We traveled all over Europe. We went to the beach for 2-3 weeks at a time. We had this country house where we spent a lot of time, and I wanted to give that to my kids, and I wanted to give it to myself too, to be honest, not just to my kids. And in academia, it's not that you have the summer off. You don't have the summer off, but you have a more flexible schedule. So I decided that I wanted to have a slightly more flexible schedule in the summer when the kids were out of school, so that we could travel, so that we could do more things, and that I did. The other thing was that IBM research went through a transformation around the time that I left. And I thought, like with everything else, good things may come to an end, and you can move on to something else. Academia has always been, and that's actually what made IBM special, was that it was a very academic place. But I also missed. So here's the student that worked on the deniable exchange. He was a PhD student at University of Catania in Italy. That was the university where I went undergraduate. And this was the second student that was sent to me to help him with his PhD thesis. They wanted to do cryptography. There was nobody there that did cryptography. And they asked me, the Italian system has money for them to spend time abroad. And so I took them in, and they were visitors at IBM, and they were taking classes at Columbia, and I worked with them. And that was one of the things that I missed. We would get amazing students in the summer. We get one or two interns, but the ability to have a one-on-one mentoring relationship with graduate students, it was something that I really missed. And so I thought it was a good time to do it. And there was a good opportunity here in New York. I didn't want to move from New York City. So I took it. And I have no regrets. I do miss the team. I do miss the ability of walking out of my office and walk into their office. But I think it was the right time.
Yeah, great. And so what's your opinions on patenting in cryptography? I mean, there have been lots of horror stories of when patenting has held things back. And you've worked in IBM, and obviously for IBM, it was important to patent methods.
Yeah.
Where do you lie with that?
So we brought up a few patents, but we weren't very aggressive. And one of the reasons was that you would adapt the publication if you wanted to patent. And so for me, the publication was more important. So that was one thing. And in reality, we were able to have conversations with managers about, if you patent this, then people will use it.
Yeah.
Right. And the Schnorr example was so recent and right. So I don't think patenting ideas is such a great idea. And so since I left IBM, I haven't patented anything. I've had this conversation. At one point, the president of my university brought in a bunch of researchers and said, should we have a strategy around patenting? And it was a uniform consensus from the researcher across all different fields, not just computer science, that no, you do your research and you if you're looking for income for the universities, the way you do it is by presenting that research to companies who want to use it and develop a partnership. And because that's a much longer term and more impactful way to benefit the university than royalties from a patent that may end up not being used, right? So I was actually surprised to see everybody else sort of agreeing on that point. So, and that's really what I think that, I mean, there are certain things where you invest, maybe drugs, medical drugs, where there has been such a huge investment that you need to maybe recoup it, and that I understand. But code and algorithms and ideas are totally different.
Difficult, yeah. I mean, obviously, a spin-out company or a startup can protect themselves in the market against an IBM or an Intel. So that's certainly one thing, and investors often look for the patents. But I don't think there's a definitive black and white when it comes to this. So what does the next decade of cryptography look like to you?
So there's going to be a lot of work on the practical side, on this like zero knowledge, full homomorphic encryption, lattices, to really bring them as close as possible to the where they're not yet ready for prime time, right? So issue like the ones that I was discussing, how do you do that for neural networks, for large language models? How do you sort of run them with privacy and authentication, given they're such massive piece of code? On the more theoretical front, I think I don't know. There is my personal. I had a little bit of revelation in the last year or so, and it's something that I'm actually starting to look at. I teach this advanced crypto class for doctoral students and maybe high-level master students. And for the last year, every time I teach it, I've had physics students taking my course. And they're not actually there among the best students in the class, but are not having. And the reason they take it is because they want to learn about not quantum resistant cryptography, but quantum cryptography.
Cryptography. Actually running cryptography on a quantum computer.
On a quantum network. So they are looking at properties of entanglement and properties of the quantum world to actually be able to transmit information.
Excellent, because there's some things you can do in a quantum space that you can't actually do in a classical
Right. So we know, for example, that you can do key exchange on a quantum network. And what else can you do? We don't know. But I mean, we know some stuff. But you can use properties of entangled particles for the two of us to establish a secure channel. And that is, quote unquote, unbreakable in the sense that there is no. So I've actually started working with one of the students. We're looking at these notions of verifiable computation. There was actually a very beautiful paper that came out a couple of years ago in this line of research. There's a powerful and there's a lowly machine that wants to verify the behavior of the powerful machine. This paper looks at a quantum computation that needs to be verified by a classical observer. So this paper has a trove of techniques that are so interesting. So anyway, but I think a lot of interesting work is going to come out from this notion of quantum information theory and quantum cryptography. And I think there is very, very exciting work there that sort of sits at the intersection. Because if quantum cryptography will be deployed, because it requires very sophisticated equipment, it will be deployed in very few places, And then what you need to do is figure out how you interface a classical world that communicates through classical means with this very powerful quantum devices. There could be a quantum computer for computation, or it could be a quantum uh, router that routes information through this quantum entanglements. But you need to be able to get the security properties guaranteed by this machine while you are running on a classical system. So I think there's
Yeah.
a lot of interesting work that's going to happen there as
Yeah.
well.
It's almost like we've hit the limit with Moore's law with silicon. We
Right,
can't get transistors any smaller and we can't go any faster and so on. So the only way we can increase our computing speeds is to move towards quantum methods, to go
right.
towards optical techniques. So my last question, thank you so much for bearing with me for this time, is if you could change one thing about your career, what would it be?
Oof. Um, well, I would talk to my younger self,
Mm.
mostly my graduate student self. Um, and I would um, tell myself to be a little more sure of myself, more
Yeah,
confident. If I had been, I think there's a lot of things that I missed
mm,
in my early career because I didn't trust my instinct. I didn't
yeah,
trust my knowledge,
yeah,
and I didn't know how to get the knowledge that I was missing. Um, and there was a lot of mental energy devoted to some sort of imposter syndrome, right?
yeah,
Uh, I'm not good enough. Why do I even
mm,
try? Those people. Why do I want to work with these people when um, they're so much smarter than me? It, if I had been a little more confident, I think um, I would have been happier. It's not
mm,
even a matter of uh, if I have achieved. I think I've achieved quite a bit in my life, and I'm
yeah,
very proud. I'm very happy with
yeah,
what I've achieved. I have no regrets, but I would have enjoyed some of the work a little
mm,
better.
yeah,
Even the ability to tell my advisor, I don't want to work on this. I mean, I tell my
mm,
students all the time, this is a very interesting problem, but I don't want to work on it.
yeah,
I didn't even have the confidence of saying that. So I
yeah,
tried to work on things because they were suggested to me, but I
mm,
never really had the confidence to see that as a
yeah,
suggestion, right? It was like it was an assignment. And
mm,
so I felt like I didn't have that maturity when I was a
mm,
graduate student and that confidence to really maybe that's what grad school is for, right?
yeah,
Maybe that's you come out of that and then you're a researcher. Um, but um, but yeah, but I think a little more trust in my own means would have helped a little better.
yeah.
Being maybe a less anxious and less stressed out.
Yeah, yeah. It's completely true. I mean, when you finish your PhD, what do you do now? If you're just waiting for someone to tell you what to do now, then you're missing the opportunity
Exactly,
of
exactly.
independent research.
The grad school is really
Yeah,
where you know you
yeah,
have to sort of develop that.
yeah. It's good.
Yeah.
Thank you so much. It's been a pleasure
Thank you.
to speak to
It's
you
a
and to go
pleasure.
back through the years and to still see that you're so passionate about the subject and so knowledgeable. It's really great for you to take these really complex topics and break them down. I think a true expert is someone who you can fire questions at and they'll break it down into small chunks that are understandable. So thank you so much for
Thank
that.
you. Thank you. That's a very great compliment.
Yeah, that's great. And hopefully, if you're in the UK sometime, you can come over to Edinburgh and we can
Never
host you
been,
for
and
an
I'd love
event.
to visit. So
That,
I'll
that'd be
take you up on
fantastic.
that.